Bem, nós queremos convidar o Dr. Tchekarchov e o Dr. Yves Fouquet para a mesa.
Geophysics, biodiversity, ecology, microbiology, both on hot vents and on cold seeps in the margin. So for this talk, I will mainly focus on the geological part, but we had several questions about environmental concern to study these different deposits. And in our group, the concern is starting at the very beginning of the exploration cruises. So then a few comments. First, general comments. The ocean covers 71% of the Earth, and 60% of this is deeper than 2,000 meters. This means that we have a lot of work to do in the deep ocean. Then this huge area is relatively unexplored. However, the scientific exploration during the past 30 years have revealed that we have various types of mineral deposits. And we are only at the beginning to appreciate if these deposits can have an economic interest. So this is just to show that what we are doing in the deep ocean and what we have been doing in the deep ocean is mainly scientific work. Then dealing with this type of mineralization in the deep seas. So we have heard during the last 2 days a lot about nodules in the deep ocean basin with copper, cobalt, nickel in relatively deep environments, 4,000, 5,000 meters. This is still a potential resource with moderate economic interest, of course, depending on the value of the different metals. Then the manganese crust in generally intraplate seamount with the cobalt, typical cobalt enrichment in addition to the copper we have on the nodules, and also for some side, some platinum enrichment. These are found between 1,000 and 2,000, 3,000 meters. They are also a potential resource, and their interest on the economic point of view is, for the moment, moderate. The seafloor massive sulfide, also called SMS, are associated with volcanic ridges, and they are characteristic in their copper, zinc, silver, and gold concentration. They are found between 1,000 and about 4,000 meters of water depth. They are potential resources, and for the moment, their economic interest is high because there is some work done by an industrial company in the Western Pacific to mine this type of deposit. So these SMS deposits are interesting because of this generally high-grade concentration in copper, zinc, silver, gold, and in some places lead and cobalt enrichment. Some deposits in terms of size are equivalent to deposits mined on land. And just a small part of the volcanic, submarine volcanic center have been studied with enough detail to locate these deposits. And I will come back in detail of the different scale at which we have to work. So a few words about the composition, just to answer one of the questions we had for the first talks. Very general table with average composition of nodules in the Pacific Ocean, average composition of the manganese crust, and average composition of sulfide deposit for the Southwest Pacific, for the Eastern Pacific, and for the Mid-Atlantic ridge. And if we look at some of the metals, for example, copper and zinc are relatively low in nodules and manganese crust. But if we look at the Southwest Pacific, it can be as high as 16%, 10% on the Eastern Pacific, and 6% in the Atlantic. This is average deposits for all deposits in these different settings. So this gives very strong weight to this different values. For the copper, the Southwest Pacific is about 3.5%. East Pacific close to be the same. And the Atlantic is characteristic for its high copper concentration. But altogether, generally, the Atlantic deposits are extremely rich in these two metals, and particularly compared to the nodules and manganese. Other interesting metals, gold and silver, which are absent from the nodules and the manganese crust, they are gold may be concentrated, so this is in value in gram per tons, 2.5 gram per tons on the Southwest Pacific, much lower, 0.6 on the East Pacific rise, and relatively high, 3.54% for gram per tons along the Mid-Atlantic Ridge, particularly in the northern Mid-Atlantic Ridge. Silver is also high, 400 on the Southwest Pacific, and lower on the East Pacific and Mid-Atlantic Ridge, but still high in terms of concentration. So I will not go further in the detail for other elements, but this is just to point that these are really high-grade deposits compared to manganese nodules and crust. Then a little bit of science to explain how this hydrothermal system works. So they are generally located on spreading ridges. So on spreading ridges, plates are moving apart and creating a volcanic ridge. And this volcanic ridge is directly connected deeper in the system at about, you have the scale here, 3 kilometers of water of depth under the seafloor, to what we call a magmatic chamber, where the temperature of the lava is about 1200 degrees. So this gives a very high increase in temperature for 400 degrees per kilometer just under the ridge crest. And as the ridge is splitting the plates, we have creating a series of faults, and the seawater can penetrate along these faults. And approaching the magma chamber, it can increase in temperature and move away because the density is lower. And during this circulation, there is a lot of exchange, alteration of the basement rocks, and enrichment of metals were extracted from the basement rocks. Then, when the fluid reaches the seafloor at 350 degrees, the fluid is rapidly cooled because the seawater is just at 2 degrees at this depth, about 3,000 meters. And the fluid is mixed in the seawater. First, the input is vertical in the water column, and then we form what we call an hydrothermal plumes that is moving with the currents horizontally at about 300 meters above the seafloor. I will come back to this when discussing the strategy to locate these deposits. So this is for the general rule, and you can extrapolate this rule for the 60,000 kilometers of mid-oceanic ridges. And during the past 70 years, we discovered several situations when we had this sulfide deposit. So historically, the first discovery was made at 21 North along the West Pacific Rise here. Then a series of exploration continued and discovered many sites along what we call the West Pacific Rise and further north, Juan de Fuca Ridge. And at this time, 78, we thought that black smoke and sulfide deposits was quite a characteristic of what we call the fast spreading ridges, because East Pacific Rise is a fast spreading ridges splitting at about a maximum near Easter Island here of 18 centimeters a year. Then this was early 80s. Then we continued to explore the Western Pacific here and here, and we started to discover similar deposits on the back of the trench. The trench is here, the green line. But in the back of the trench, there are short volcanic lines where you can also find some hydrothermal deposits and black smoker deposit. And more recently, but the first sites were discovered in '85 on the Central Atlantic here. We demonstrated that the black smoker story and sulfide deposits was not only a characteristic of fast spreading ridges, but also a characteristic of slow spreading ridges. This means that you can expect to have hydrothermal sulfide deposits everywhere where you have this type of volcanoes, magma chamber, heat source, energy to drive this hydrothermal circulation. Then in terms of type of deposit, I have no time to go in the very details, but you see there are some blue color, green color, yellow colors in the different sign. The color is dealing with the base composition of the basement rocks, and I explained before, the metals are extracted from the basement rock. So depending on the type of the basement rocks, you can expect different composition in the deposits. We have basaltic rocks, rocks from the mantle, acidic rocks or silicic rocks, generally in this small ridge on the back of the trenches, sediments, and this gives different type of combination, giving quite a wide diversity in this type of deposits. Then for this exploration in France and at Ifremer particularly, we started the story at the very beginning because we were in the group discovering the first site with a US scientists at 21 North. So we have worked a lot on the East Pacific Rise, north and south. Some cooperation with Canadian group in the Juan de Fuca Ridge. In the late 80s, early 90s, we work on the Southwest Pacific, cooperation with Japan, cooperation with Germany. And more recently, we had several European-funded programs south of the Azores area, and a continuation of the cooperation with a Russian group, with Georgie here, on the further south around 13, 15 north on the Mid-Atlantic Ridge. Then this is what we know for the moment. Now I will go further in the detail and showing what are the difference between a fast spreading ridge and a slow spreading ridge like the Mid-Atlantic Ridge, just to show and discuss what we are expecting, for example, on the South Atlantic Ridge. So first, what's happening on a fast spreading ridge? I will show just one site here at 13 north of latitude on the West Pacific Rise. So on a fast spreading ridge, what you have, just look at the scale. The scales are very important. This is the ridge, 300 meters high. This is the line where the different plates are splitting apart in two parts, and you have a small depression here. But this depression is just 500 meters wide and 50 meters deep. So it's just a line. But on the side, we see some volcanoes, and very young volcanoes starting to be born on the side of the ridge. So when you dive on this ridge, what you see is quite a large number of hydrothermal vents, active or inactive, and this is a detailed view of this part. The depression fault are here in black, and all the dots and triangles are individual hydrothermal sites. So on a very short distance, here it's about 15 kilometers, you have several tens, even several hundreds of deposits. But in terms of ore deposits, these are very small. And then if you move away on the off-axial volcanoes, in this place, for example, this small spot here, enlarged on the cross-section here, you have a pit crater on the top of the volcano, and on the side, here this yellow triangle, it's a large ore deposit, 200 meters across, about 50, 60 meters wide, and this is about a few million tons of massive sulfide. So this means that on the ridge axis itself is not quite interesting in terms of large deposit, but off-axial seamounts have some interesting potential. So just remember the scale, and it's say some kind of mono-dimensional way of looking for vents. You have just to follow the line. So it's easy. So if we continue to summarize this on the East-Pacific Rise, you have transform faults here, a series of volcanic segments about 20 kilometers long, and generally the vents are more or less at the central part of these segments. And it's very simple. You have just to follow a line, and you find the vents at the central part or on a axial volcano. So to summarize, fast spreading more than 6 centimeters a year of spreading rate. They are stable. The hydrothermal system are stable for a few years to a few tenths of year, so it's very short. The fluid composition in terms of metals, for example, may change rapidly in a few months. Deposits are numerous, more than 100 on the 20 kilometers long ridge, but very small at the segment scale. The spacing of the deposits can be about 100 meters, and they are aligned along a very narrow line. Okay, this is for the fast spreading ridge. Now if we move, and there is a strong volcanic control, they all are located on the top of the volcanic ridges. And possibly this large off-axial deposit. Now if we move to slow spreading ridges, south of the Azores, and if we look at the three-dimensional map again, you see here that it's more complicated. It's more complicated, and you have a series. For example, here we have one volcanic segment, a discontinuity, one volcanic segment, a discontinuity, another volcanic segment, discontinuity, volcanic segment, discontinuity, and volcanic segment. And what is the scale compared to what we have just seen? This volcanic segment is about 60 kilometers long. The Rift Valley is 20 kilometers wide compared to 50 meters wide on the East Pacific Rise, and the Rift Valley wall here are about 1,000 meters deep. So the scale is completely different. So we have done expression. So when you start with such a map, where you go, where to find vents. So you need quite a lot of time, and I will explain the strategy later. But we have found vents there. We have found vents on the top of the volcanoes as a central part of the segment, but also vents, low temperature here, and on the discontinuity, on the southern part of the segment here again, and here again. So this means that we have what we call volcanic control here, but also a tectonic control on other side of the on the southern part of the segment. So it's much broader and much difficult to find. So the deposits are also much bigger compared to the axial deposits on the West Pacific Rise. A typical deposit here is a tag deposit on the Mid-Atlantic Ridge at 26 north. So the massive sulfide here, this part, 200 meters across, 50 meters high, and in this deposit there is a zonation in terms of concentration of metals. The copper-rich part is directly rooted on the black smoke and chimney. The zinc-rich part is located on the side, very close to the surface, and the rest of the deposit is mainly iron-rich and not very interesting in terms of ore deposit. So if we summarize now for a slow spreading ridge, 60 kilometers long, 20 kilometers wide, 1 kilometer deep, generally a volcanic center as a central part, and so now we are able to see that there are deposits at the top of the ridge, on the volcano, at the base of the Rift Valley wall, on the side of the Rift Valley wall, very often related to transversal faulting, but also on what we call the non-transformed discontinuities, and also on what we call the inside corner intersection between the ridge and the major fracture zone. So this is quite a broad area to explore if you want to find vents. But now we start to have some clear idea to see where they are. So to summarize, low spreading ridges, 6 centimeters, less than 6 centimeters a year, stable for several thousand or tens of thousands of years. Georgie will say some words about this duration. The fluid composition is stable. There are fewer but larger deposits, typically several hundreds of meters in diameter. The spacing is more important, more than 50 kilometers compared to maybe 50 meters on the East Pacific Rise. And both the volcanic and tectonic control of the hydrothermal discharge. Now, considering this knowledge, what could be the potential in the South Atlantic Ridge? So first, we have just to look at the map again. We see that with the exploration we did on the North Atlantic, we have about 12 major high temperature sites. There are few sites discovered recently by the German group on the just south of the Ecuador. But as the Mid-Atlantic Ridge is spreading at the same rate, more or less, all along its length, from north to south, we have just to expect to find a similar deposit in the Southern Atlantic. So what we don't have deposits there. So I've just looked rapidly at the IFREMER database about the cheap track for multi-beam mapping on the Mid-Atlantic Ridge. And we end with this type of map. We see clearly the Mid-Atlantic Ridge, the northern part of the Mid-Atlantic Ridge, with a lot of ship operation. And if we look at the similar map south of the Atlantic, okay, it's not all the data are there, but something is missing in terms of map. So the potential is interesting because it's a slow spreading ridge. So the first point is to consider that we may find the same thing that this deposit we have on the Northern Atlantic. So same potential as the North Atlantic Ridge. Very few sites are unknown. So far we have 2 sites. Very few maps exist. There is some interest for the biologists in terms of biodiversity. You have also to consider these multidisciplinary studies. And for continuing the